Hello everyone, and welcome to today's webinar on electrical safety testing, circuit theory. I'm your presenter, Syed Abidi, and also helping us today is Jim Kennedy with any technical issues. A few notes before we actually begin with our presentation. This webinar is actually the re-recording of our webinar that was originally presented on August the 13th. We are re-recording this webinar because we faced some technical difficulties during the recording of our previous webinar, and there were some disturbances, so we wanted to ensure that the presentation that we put up on our web page is free of any of those troubles. So once again, this is a re-recording, and we're going to be covering electrical safety testing circuit theory in this webinar. So with that said, I'll go ahead and begin with our material. So just a quick overview of what was covered in our previous webinar, which was presented by Nick Piotrowski, and the topic for that webinar was ground bond and ground continuity testing. And some of the topics that were discussed during that webinar were the grounding of electrical products, the Class 1 and Class 2 products, ground continuity testing, and ground bond test. We will quickly cover these or revisit some of these concepts that were covered in the last webinar in today's webinar as well. So it'll be a good review for those who missed out on some of that material. So here's an outline of what we will be covering today. We will start with a review of the basic electrical safety tests and try and understand what is actually tested during each of those tests. We will then try and understand the circuit theory behind the electrical safety test, and we will also touch upon some of the features of associated research electrical safety testers, such as arc detection and Smart GFI circuits. And then we'll leave and of course there won't be any questions because this is a re-recording. So, starting with our common electrical safety tests. The first and the most basic of all the tests is the ground continuity test. The next one is the ground bond test. Then the dielectric withstand test, also commonly known as the HIPA test. And also it is the most common type of electrical safety test. Then there's the insulation resistance test. And lastly, the line leakage or the touch current test. So starting with the ground continuity test. Well, the ground continuity test is often required to be performed with the dielectric voltage withstand test or the HIPA test, but unlike the dielectric voltage withstand test, the ground continuity test is not an insulation test. Instead, its purpose is to ensure that the DUTs, or the device under test, safety ground connections have been made properly. Grounding electrical equipment provides a second line of defense against electric shock over and above the basic installation of a product. And this grounding of the metal enclosures or exposed dead metal on the equipment also establishes a common ground or earth reference between multiple pieces of equipment which may be in close proximity to each other. A ground continuity test is normally required as a 100% production line test on electrical equipment in order to verify that there is continuity in the ground circuit of the device itself. If or when an insulation fault develops between the line circuit and the exposed metal parts, the ground conductor provides a path for the dangerous fault currents to return to the system ground. at the supply source of the current. And if this ground circuit is of a low enough impedance or resistance, the current will circulate through the ground conductor of the equipment, and thus enabling the circuit breakers or fuses to open. By grounding the exposed metal parts, all normal leakage current is or can be safely routed to ground and does not flow through people who touch the product. So this is how it protects the user. And one thing to consider here is that this system, the grounding system, only works if the user does not defeat the safety ground. Often we've heard of users, they end up defeating the safety grounds by removing the ground prong from a plug or by using an ungrounded 3 to 2 prong adapter box. Because these practices are so common, products with 3-prong line cords are still required to pass the dielectric voltage withstand tests, just as the ungrounded Class 2 products. And the integrity of the ground circuit is what protects the operator if a fault should occur in the installation of a Class 1 product. So ground continuity test is, of course, performed on products that have a ground circuit, or in other words, a Class 1 type products. Now, the ground continuity test, does have its shortcomings, and the ground connection, such as the ground connection to a product, should be rated to handle its nominal input current in case a fault occurs, and the line voltage becomes present on the product's metal enclosures. Some testers equipped with ground continuity function only give an indication if the continuity is present. Therefore, if the test operator has no way of knowing the impedance or the strength of the ground connection, a ground continuity test could very well pass a product that has only one strand of wire, for example, connecting its chassis to ground. If a fault were to occur, this connection may not be capable of handling the input current to the product and could create an open ground condition and a shock hazard. For this reason, many electrical product manufacturers have been turning to the ground bond test, as a more thorough alternative to the ground continuity tests. So the ground bond test, or the ground impedance tests, can be used to determine whether the safety ground connection of a device under test can adequately handle the fault current resulting from a dielectric breakdown. By simulating a failure condition and circulating excessive current through the device's ground connection, the ground bond test helps to verify the integrity of the connection to earth ground. So therefore, if a product's insulation fails, the low impedance, this low impedance ground connection should be sufficient to handle the lethal fault currents that will flow to the ground, and hence it will protect the person that comes into contact with the device's metal enclosures. So the big difference here between the ground bond and the ground continuity test can be considered as the ground continuity test will only give us, or will only tell us if the ground circuit of a device is continuous or not, whereas the ground bond test is the one that will tell us how good or how solid is the ground connection. Here's a little diagram that shows how a ground bond test circuit looks like. So on the left-hand side, you can consider the box on the left-hand side as the ground bond tester, and on the right-hand side is the device that is being tested for ground bond test. And as you can see, it's got a 3-prong plug or a line cord, hence making it a Class 1 product. And from this picture, you can see that the way the ground bond test works is that it injects high current into the ground pin of the device under test, and that high current flows through the ground circuit onto the chassis of the product, and the return connection is made at the surface or the chassis of the device under test. And the Kelvin method is what is used to measure the resulting impedance of the ground circuit. And the Kelvin method is basically a standard 4-wire measurement method that's used during a ground bond test to eliminate the inherent test lead resistance from the test results. As you know, test leads add up their own resistance to the entire test system, so it is very important to negate that impedance. The Kelvin method, it provides a more accurate resistance measurement, which are crucial when dealing with minuscule resistance values measured during a ground bond test. And now this is why the reason for this is that for a ground circuit to be effective, we want, or any manufacturer for that matter, would want their product's ground circuit to be of low enough impedance, so it is capable of handling all that fault current and routing it to the ground. So this is what a ground bond test would look like in terms of its circuit. And next we're gonna look at another circuit for the ground bond test, and here what I just talked about, how the high current is being injected. You can see the dashed green line is what's showing the high current being injected into the DUT's ground pin from the line cord, and it travels through the ground circuit into the chassis of the product, which is of course the chassis or the dead metal is making a solid connection to the ground pin, and the resulting impedance is being measured by the ground bond tester itself. Here we're showing a fail condition for a ground bond test, meaning that in this case the ground bond tester has detected a failure, or in other words, it has detected that the ground circuit of this product was not capable of handling all the fault currents that were imposed upon it as a result of insulation failure. Now, a few other things to consider about ground bond tests are that it is commonly referred or considered a type test, meaning that it is usually performed during the development phase of a product, but it could also be a production line test. It really depends on the standard that the manufacturer is trying to comply with. The results of the ground bond tests are displayed in ohms, and again, here's a picture showing a simple handheld drilling machine being connected to one of Associated Research ground bond testers, the high amp 3 series of testers. And as you can see, the red connection is connected to the ground pin of this device, which is basically indicating that this is where the high current will be pumped in to the ground pin of this device. And on the right side is the return, showing the return circuit. To complete this circuit, the return connection is one end is plugged into the tester, the other end is clipped or plugged onto the product's chassis, a good chassis point. Test parameters for ground bond tests can vary from standard to standard, so it is always a good practice to refer to the standard that the manufacturer is trying to comply with. And it is a high current test, and it is a high current test and a low voltage test. So and it can also be required to be performed in AC or DC based on the product and the safety standard. Again, if whenever in doubt, safety standard is your best resource to look for test parameters and types of tests that are required to be performed for the product that you're trying to test. Next, we're going to look at the dielectric withstand test, or more commonly known as the high-pot test. Well, this is one of the most common of all electrical safety tests that we will cover. The dielectric voltage withstand test, or the high-pot test, is performed by electronic product manufacturers. Basically, it's designed to stress a product's insulation far beyond what it would encounter during normal use. And the assumption is that if the insulation can withstand a much higher voltage for a given period of time, it will be able to function adequately at its normal voltage level for the life of the product. Hence the term voltage withstand. And here is at the bottom of this page you can see a picture that's showing how the circuit for the dielectric voltage withstand test looks like. So on the left side you can see an Associated Research Omnia 2 series of electrical safety compliance analyzers, and on the right side we can assume that this is the device that is being tested. The high-pot test is used to detect possible defects in the design of a product and workmanship defects, such as inadequate creepage or clearance distances. So it can give the user a lot of good information. But in addition to overstressing the insulation, this test can be performed or is also performed to detect material and workmanship defects, as I just talked about. Most importantly, small gaps, gap spacings between current carrying conductors and earth ground. When a product is operated under normal conditions, environmental factors such as humidity, dirt, vibration, shock, and other contaminants can close these small gaps and allow current to flow. This can create a shock hazard if the defects are not corrected at the factory. And no other test can uncover this type of defect as well as the dielectric voltage withstand tests. And shortly we'll show you a quick video of how a ground bond test and a dielectric voltage withstand test is performed. But here is a quick, circuit, or so to say, how a dielectric voltage withstand test, when it's performed, what happens on the device that's being tested. So, looking at this picture, we can see that the high voltage coming out of the top side of, if you see the white connector on the tester, high voltage, this is where the high voltage is outputted. And where is it applied? It is applied onto the mains conductors or input conductors of the device that's being tested. In other words, high voltage is applied by shorting line and neutral pins on the device's line cord. So by shorting the line and neutral, high voltage is applied, and this is how the insulation of the device is stressed. The high voltage is applied between the mains conductors and the metal chassis of the product. So what happens here is that as the high voltage is applied on the by shorting line and neutral, a leakage current, a resulting leakage current flows due to the application of this high voltage. And this essentially creates a large capacitor. So think of the device that's being tested, that's being tested for dielectric voltage withstand test. It actually turns into a huge capacitor. Why? Because a capacitor is essentially two conductors separated by an insulator. And if you look at this picture, what we're trying to show here is that we even have two signs of symbols for capacitors on the, I'm sorry about that, insulation side, between the insulation and the mains conductors. So the reason for showing these capacitor symbols is that because essentially when the high voltage is being applied on the mains input, between the mains input and the chassis, the product under test is being turned into a large capacitor. There's going to be a potential difference, a huge potential difference here, and the resulting leakage current will flow as a result on the chassis of the product. The return side of this, the return connection back to the high-power tester is made at the chassis of the product or the ground stud of a product. Some products have a ground stud in the back, which if the casing is all plastic, or if the casing is metal and it makes a solid connection with the chassis, the return connection can be made at the chassis itself. So the resulting leakage current is measured by the high-power tester on the left side, and here's a simulation of a fail condition for a high-power test. In this picture, we can see that when the high voltage was applied to the mains conductors, the resulting leakage current that flows was too much for the insulation. Basically, this is showing a breakdown condition, and during a breakdown, what's going on is that the insulation has basically fallen apart due to the result of such a high application of such a high voltage, and excessive leakage current is flowing on the chassis of the product, hence putting the operator under the risk of a shock hazard. So this condition is showing a breakdown condition during a high-power test. Now, the purpose of a high-power test is to check for excessive leakage current flow through a product's insulation. Under normal conditions, any electrical device will produce a minimal amount of leakage current due to the voltages and internal capacitance that's present within the product. Yet, due to design flaws or other factors, the insulation in a product can break down, resulting in excessive leakage current flow. This failure condition can cause shock or death to anyone that comes in contact with the faulty product. The dielectric breakdown, on the other hand, is can be defined as the failure or the complete failure of an insulation to effectively prevent the flow of current. Sometimes it's evidenced by arcing. If the voltage is raised gradually during a high-power test, breakdown will begin at a voltage level where the current flow is not directly proportional to voltage. When the breakdown occurs, especially for a long period of time, the next gradual application of voltage often causes a breakdown to occur at a lower voltage than initially measured. The best indication of dielectric voltage breakdown or dielectric breakdown is a leakage current measurement significantly higher than the nominal current measurement. And the maximum leakage current is dependent upon the test voltage. Therefore, the leakage current trip setting will vary depending upon the product being tested and the capacitance of that product. So capacitance plays a big role here. Highly capacitive products may exhibit a slightly different behavior. The dielectric voltage withstand test is performed on both Class 1 and Class 2 products. Why? Because both have a layer, at least one layer of insulation that needs to be stressed or tested. Class 1 products have an additional feature which is the ground pin or the ground circuit, protective ground. But Class 2 products which don't have a ground circuit have a dual layer or second layer of insulation. The dielectric withstand test can be performed both in AC and DC mode based on the safety standard, and the test parameters and the voltage settings and thresholds, failure settings are all based on the standard that you're trying to comply with and the manufacturer themselves. They should know what to set for their failure settings for each test. And yeah, so this is the high pot test or the dielectric voltage withstand test. And real quick, we're going to take a look at a video. In this video, we're going to look at how a high voltage high pot test and a ground bond test can be performed. What we're looking at right now is are the cables that will be used for this test: the high voltage lead, the return lead, and the current lead for the ground bond test. So here is we are connecting the return lead to the return side of the high pot tester, and this return lead is being clipped onto the chassis of the product under test. Next, we're going to connect the high voltage output lead. Now this is what applies the high voltage to the mains. As you can see, the mains input of this DUT are shorted and the high voltage is connected to the mains inputs. And here is the high current lead used for the ground bond test, and this is connected to the ground of the product. The test is initiated. A current of 15 amps flows through the device under test, and let me just go back here a little bit. So I'm going to pause it right here at the test results so that you guys can see. What happened here is that the ground bond test was run at 15 amps for 5 seconds, and the resulting milliohm reading was 32 amps, as you can see on the screen. Whereas the high pot test, an AC withstand test, was run at 1240 volts and for 1 second, and the resulting leakage current was measured to be 0.042 milliamps. So that was a quick demonstration of how a high pot test and a ground bond tests are performed. Once you have all the connections made, it's as simple as pressing the test button on the tester. And more details on ground bond and high pot test can be found if you visit our webinar archive page on our Associated Research website. We have all these. We've performed webinars or presented webinars on each of these tests. So there's actually 2 webinars on high pot test itself. So we've covered it in quite a bit of detail. That's why we're not going to go into too much details for this presentation. Same goes for the ground bond and the ground continuity test. In the previous webinar to this one, that was which was focused on just on ground bond and ground continuity tests. So a lot of detail was covered. So if you need more information or more details on any of these tests, feel free to access any of our old webinars. And we have many upcoming webinars which we'll talk about shortly. But to continue with our presentation here, we will now go back to what we were talking about. We'll now look at the insulation resistance test. This is the 3rd test that we're covering today, and This is very similar to the DC dielectric withstand test, because this actually applies a DC potential, and it stresses the same insulation on a product as the high-pot test. The insulation resistance test is used to provide manufacturers with a quantifiable value for the resistance of their product's insulation. And the insulation tester applies a DC voltage across the insulation of a product and measures the corresponding leakage current, which is used to then calculate the resistance of the insulation. So basically the concept is the same. The high potential is applied at the same place by shorting the mains input conductors of the product under test, just as the high pot test, only that this is in DC potential, and the test voltage is relatively lower than the high pot test. And although most insulation resistance testers have a variable output voltage, this the test is usually specified, if you go by the standards, it's specified to be performed at 500 or 1000 volts. And although the insulation resistance test is related to a high pot test, this test provides more information about the device being tested, which can be useful in certain applications. The insulation resistance test also is sometimes called out by the safety agencies to be performed subsequent to the high pot test to ensure that the product insulation was, is still intact after going through a series of, high voltage tests. Insulation resistance tests are always performed using a DC voltage. This is due to the real and the reactive current components produced as a result of the device's dielectric. And in this case, the dielectric of the device is the product's insulation. When a DC potential or voltage is applied to the DUT, it negates the reactive or the imaginary current components caused by the product's capacitance and allows the insulation resistance tester to perform a true real current measurement. So once again, if you're interested in understanding the difference between a DC and an AC high voltage test, I would definitely refer you to the high pot test webinars. But the DC potential, whenever a DC potential is applied, it will negate the reactive current component caused by the product's capacitance, and it will only allow the insulation resistance test to perform a true or real current measurement. If this was not the case, the insulation resistance tester would produce erroneous resistance measurements with consistently lower values. So the insulation resistance test is also a very important test, and as far as the circuit for the insulation resistance test goes, you can think of it as exactly the same circuit as we saw for the high pot test previously in our previous slides. So once again, the high potential is applied by shorting the line and neutral, so to say, of a three-pronged line cord of the device under test, and the return lead is connected to the chassis point. However, the result of the insulation resistance tests will be displayed in ohms or mega ohms instead of leakage value, which is more common for a high pot test. Again, the test parameters for the insulation resistance test are provided by or is called out in the standards that you're trying to comply with. So I would always, refer to that. Here's a little picture in the bottom showing a insulation resistance test being run on a small transformer. And what's going on here is that the red wire connection is where the high voltage is being outputted from the tester, and it's applied to the primary side of the insulation of the transformer, and the return connection, the black wire, is connected to the secondary side, and the result will give a value of the insulation in mega ohms. Okay, so now that we've covered most of our electrical safety tests, the last one that we did not touch is the line leakage test. Well, the line leakage test is very different from the rest of the electrical safety tests that we just talked about. The line leakage test is performed on electrical products to measure the leakage current which would flow through a person while the product is operating. So here is the key. Here's the big difference between the line leakage test and all the other safety tests, is that this test is performed while the product is actually powered on or running. A measuring device, or an MD for short, is used to simulate the impedance of a human body under different conditions depending upon the application of the product. And the test is run under both normal and single fault conditions and reverse polarity on the input line. So basically, the line leakage test is performed while the product is operating, and a bunch of different fault conditions are inserted to simulate real fault conditions that may occur on the input line of the device that's being tested. So the tester, the Associated Research has come up with the line leakage testers that are capable of inserting these fault conditions to simulate a real fault and how much current will flow through a human body as a result of those fault conditions. This test is most commonly performed on medical equipment, and here's a typical circuit for the line leakage test, and as you can see on the left side is what we're trying to show as the line leakage tester. On the right is the device under test, DUT. And as you can see, the line cord, the three-prong line cord, is being plugged into the electrical safety tester, and you can also look at three different switches, S1, S2, and S3. These are what would be used to simulate or insert fault conditions during the line leakage test. So fault conditions such as open neutral, reverse polarity, or open ground. So these conditions can be inserted during a line leakage test to make leakage current measurements. And like I said earlier, the measuring device is what basically simulates the impedance, the human body impedance. So every standard that you're trying to comply with has its own MD, or measuring device, which is configured slightly differently. Here in this picture, we're looking at the measuring device from the EN IEC or UL 60601-1 standard, which is the big standard for the medical electrical equipment. And this is the measuring device or measuring circuit for that's called out by 60601-1. However, this can vary if the standard changes. This can vary quite a bit. So, so the measuring device plays a very important role in line leakage test in terms of simulating different types of human body impedances under different fault conditions. Next, we're going to look at some of the patented Associated Research features and functions that are available in most of the Associated Research safety testers. And we're going to start with the arc detection feature. Now this arc detection feature is basically, arc detection itself basically is it's not an exact science. It's got so many variables that it becomes more of an approximation than a science. But Associated Research has come up with a very smart way of measuring, arcing conditions during a high pot test. So once again, arc detection is a feature that is a part of the high-pot or the dielectric voltage withstand test. This means that arc detection is performed during a high-pot test. Now, in order to understand how arc is detected, it is important to understand what is arc detection and what is arc itself. Basically, arcing is defined as a momentary partial discharge due to the intense concentration of a high voltage electric field across a dielectric. Now, dielectric again in this case is the insulation of the product that's being tested. Many times arcing conditions can be seen as a luminous discharge caused by the ionization of air molecules, also called corona. High impedance arcing is a temporary condition, and it is not necessarily considered a sign of dielectric breakdown. The condition, which is basically the condition that a high-pot tester, is designed to test. Dielectric breakdown causes a massive amount of leakage current to flow through a product's insulation, while arcing usually produces momentary spikes in the nominal leakage current waveform. Arc detection circuitry that Associated Research has implemented is what we're going to discuss next. But before that, let's take a look at these spikes that I was just talking about. And as you can see, these spikes, they ride on top of the sine wave, and they're very short duration. And so the question here comes that how is an arc detected? Now that we understood what is arc and what is an arcing condition, we want to know how is this condition detected. Well, high impedance arcs and corona generate high frequency current pulses that ride on the lower frequency wave of the applied test current waveform. These pulses may have a frequency ranging from less than 30 kilohertz to more than 1 megahertz, and they may be very short in duration. Many times these pulses last much less than 10 microseconds, and that's what we're trying to show in this picture that you're looking at. So how does arc, how does the Associated Research electrical safety tester detect an arc? Well, looking at this picture, the Associated Research arc detection circuitry basically consists of a high-pass filter circuit that responds only to frequencies greater than 10 kilohertz. Then these high-frequency signals are fed into a comparator and checked against an operator-programmed sensitivity level, which is selected during the test setup. So as in the picture, you can see that the sensitivity level is user adjustable. If this level is exceeded, an interrupt signal is fed into the CPU, which shuts down the high-pot immediately. The arc detection failure displayed by the high-pot tester is separate from a high-pot failure or a high-limit failure or a breakdown that occurs during a high-pot test. So do not confuse arc detection with high-pot. Although this is a feature within the high-pot test that can be activated or deactivated depending on if you are looking for arcing conditions or not. But the arc failure does not mean a high-pot failure. These are two different things, two different failures, two different phenomena. High-pot failure refers to usually a breakdown or excessive leakage current flowing, whereas arc detection is a momentary condition. So it should not be confused. even if, so for example, if during a high path test an arc failure occurs, that does not mean that the high path test itself has failed. It is just the arc detection that has detected an arcing condition during the high path test, and that does not mean the high path test was did not pass. So why is arc detection important? Well, an arc causes momentary high-frequency current spikes that ride on the low-frequency current waveform. Although these current spikes may not be the result of a catastrophic breakdown of the device's insulation, they could indicate a problem with the insulation system that might become a safety issue at a later date. So, for instance, sometimes arcing can occur as a result of a series of fault conditions, usually stemming from a manufacturer or manufacturing defect such as a loose connection. A series fault condition basically creates an arc that is current limited by the impedance of the circuit it is in series with. So since the arc is current limited and this condition will never trigger the high limit failure monitored by a standard high path test, but it could create a potential fire hazard. Without arc detection, manufacturers of products with inherent arcing conditions could potentially pass faulty products or products that may fail prematurely. So now the question comes, when should arc detection be used? Well, that's a very difficult question to answer because there's not very clear requirements. There are not clear-cut requirements for arc detection in any of the safety standards. From a quality standpoint, of quality control standpoint, more information is always useful in determining product safety. And perhaps several products have been damaged during shipping, resulting in poor gap spacing between a conductor and the insulation. This condition may not result in a dielectric breakdown, but with arc detection turned on, it would be possible to catch this problem before the faulty products find their way into the customer's hands. So again, it is basically and it is puzzling because there no specific arcing standard defines whether or not arcing is acceptable in electrical products, and if so, to what degree is it acceptable. But so basically it comes down to, it's ultimately up to the manufacturer to determine whether or not to use the arc detection, and if so, at what sensitivity level it should be used. So again, as we saw, arc detection is a feature that Associated Research has added or has on its high path testers, but it is not the requirement for the arc detection is not very clear. So it is it comes down to the manufacturer. Next, we're going to cover the smart, another patented Associated Research feature, the Smart GFI, or the Smart Ground Fault Interrupt. Well, Associated Research's Smart GFI automatically recognizes the device that's being tested. It recognizes the configuration, and it automatically enables or disables the GFI circuit. In the case that the device under test is earth grounded, the return ground sense circuit automatically disables the GFI circuit and the instrument operates in a grounded return mode of operation. This mode allows the user to perform their tests normally without the operator having to manually change the instrument's configuration. Now, it is important to note that even though the Smart GFI is disabled in grounded mode or return mode, it is most likely because the device under test case is grounded. This in itself provides a level of safety and security for the operator, since during a fault condition, the current will bypass the operator and return directly to the source, even if they were in contact with the device that's being tested. However, unlike the conventional GFI systems that we see in in our households, wall outlets, the Smart GFI, so unlike the conventional GFI systems, once the test conditions change from grounded return back to floating return, the Smart GFI circuit will automatically be enabled. And unlike the conventional GFI circuits, the Smart GFI does not use a comparison measurement for detection of ground fault current. Since this circuit can automatically enable and disable itself, it can be set up to monitor actual fault current through the ground. Now, this feature greatly simplifies the circuit, and it improves the overall reliability of the Smart GFI. The Smart GFI circuit, will shut down if high voltage, if leakage to ground is, detected, and in some associated research testers, the Smart GFI trip level is fixed to 450 microamps, but in others it is also user adjustable, so it can be adjusted from, starting from 0.4 to about 5 milliamps. And it is a high-speed shutdown circuit that disables the high voltage in less than 1 millisecond. Now, let's look at this picture, or schematic or a circuit diagram for Smart GFI. Many testing applications are very versatile, and and production lines can quickly be reconfigured to manufacture and test a wide range of different products. In some cases, these products might be grounded via a production roller platform requiring the return of the electrical safety tester to be grounded, and on the others, the return may be floating. The Smart GFI ultimately provides the most effective safety protection, since it is an active circuit, and it is constantly monitoring the configuration of the return connection, and it's automatically adjusts itself accordingly. And by eliminating the operator from the equation of the Smart GFI works as an effective safety circuit because it does not require human interaction that could invite the possibility of operator error. So that concludes our presentation for electrical safety test circuit theory, and I hope you guys can take advantage of this presentation, and the material that was presented in this presentation was of help. I would highly recommend that you guys continue to join us for our upcoming webinars in 2014. The next one will be on insulation resistance testing. So for those of you who are interested in understanding more details about the insulation resistance test, please feel free to register for our upcoming webinar. And with that, I will once again, I would like to thank you all for those who attended the original webinar that was aired on August 13th. Once again, this was a re-recording that we had to do due to some technical difficulties. And if you have any questions regarding the presentation of this webinar, or if you need a copy of this presentation, feel free to contact Jim Kennedy at asresearch.com. Also, you can visit our website at asresearch.com and email us with any questions regarding any material that was presented in this webinar, or any general questions on our product line, or any application questions. So once again, this is Syed Abidi signing off, and we will see you next time. Thank you very much for attending and being patient for our webinar.